Hello everybody, this is lesson 2 of the Forces unit, and this time we are looking at scalars and vectors in Fring. So our objectives today are, I can explain the difference between a scalar and a vector. That objective is very important. I can draw accurate free body diagrams, which builds up on last lesson's work, and I can state Newton's third law of motion and be able to use it. So last lesson we learned about different types of forces and how to draw simple free body diagrams. Today gets a little bit more interesting. So let's look at Shepards, Barton, Junction. So you're going to see a skateboarder and he's going to push himself to go faster and faster. Let's see where he goes. There you go. Did you see him? So talk to someone around you, or just talk to yourself if you're isolating at the moment. What did you see happen? What happened? Well, if you said he travelled down the steps and into the candle shop, then really good, well done, because you've been talking about direction. If you said he moved really fast down the steps, then well done, because talking about the speed is all about magnitude. So how do we explain this in terms of scalars and vectors? A scalar only has magnitude. For example, the skateboarder has a speed of 5 meters per second, and you probably know this already. It's written as 5m/s. Don't ever write mps, that means something different. So 5 meters per second, 5 and then m/s, so /s. So scalar has a magnitude. There he is. And if we said he had a magnitude of 5 meters per second and he went forwards, now we've got an associated direction as well. And that means it's a vector quantity. So scalars have magnitude only. This is like a number. So 5 meters per second. Okay, that's all the information it tells us. It just tells us an amount, and that's what magnitude means. But a vector has a magnitude, the amount, and it also tells us which direction it's going as well. So it could be forwards, backwards, north, south, something like that. So scalar has one piece of information, a magnitude. Vectors have two pieces of information, a magnitude and also a direction. Okay, so let's have a look at our market day. So there are many names of scalars and many names of vectors. You do need to know some of these off by heart. I mean, this will get much easier as you work through year 10 and year 11 as well. But if you can remember some of these off by heart, then you'll be doing very well to prepare yourself for later years. So to list some scalars, speed we've already met, like 5 meters per second, or distance, like 10 meters, or mass, 75 kilograms, energy, 1000 joules, time, 30 seconds, volume, 25 centimeter cubed. So all of these you should have seen or used before. All of these have magnitude, none of them have direction. Okay, they all have a number, an associated number, what we call magnitude and amount, but we have no idea which direction either of these are going. And you might have walked past a blue house clock on your way to school, or you probably know where it is. This is also an example of a scalar quantity, the clock, because you just see a number. It just tells you the time. So that's a scalar quantity. So let's have a look at some vectors. So vector quantity could be velocity, or weight, or displacement, or force, or acceleration, or momentum. All of these have a magnitude and also a direction. But when you see the word, let's take the top one, velocity, such as 5 meters per second, it's hard to determine whether that's a scalar or a vector just by looking at the word. So usually there'll be a diagram with an arrow to show you a direction. So let's have a look at that now then. So there's a horse. What's it doing in market day? Oh my goodness. So it has a magnitude, which will be shown by the length of the arrow. The longer the length, the greater the magnitude, and we met that last lesson. Is that? So speed and velocity both have the units meters per second. So what's the difference? So let's have another look at the horse again. So the people down here say this horse has a speed of 5 meters per second. This has been represented as a scalar. So motion here, the movement, the motion is a scalar. Whereas lady down here, she's saying this horse has a speed of 5 meters per second flying upwards. So now she's represented the motion as a vector because she said the magnitude, the amount, 5 meters per second, but she's also provided a direction as well. And then she said it was upwards. So the horse there has been represented by a vector quantity because there are two pieces of information. So physicists make everything really easy. Physicists are not known for their art skills, drawing horses, combine harvesters, everything like that you find in a market or in a field around the room. It just makes life easier if we just draw what's called a box and arrow diagram. So here are two boxes, and the boxes could be anybody. It could be anything, but we just represent it with a box. So the arrows here are always drawn to scale, and it'll be a good habit, and you'll get lots of practice of drawing these arrows to scale. And you can see the one on the left is 1,000 newtons pointing to the right, and the one on the right is 500 newtons also pointing to the right. 500 newtons is half of 1,000 newtons, so the arrow is half as long. And that's assuming we've used the same key for both. To scale this properly, we need to use a ruler and a key. So let's see how we're going to do this. My key was 200 newtons for each centimetre. So the arrow on the left is going to be 5 centimetres. So if it's 1 centimetre for 200, 2 centimetres for 400, and so on, we get to 5 centimetres for 1,000. And we can see in the ruler, every centimetre is worth 200, so 5 centimetres is 1,000. And if we look at the one on the right, then we get to 2.5 centimetres. So every centimetre is 200. The first one's 200, second one takes us to 400, and then half a centimetre is 100, which gives us 500 altogether. So this is your opportunity now. So you're going to pause the video in a moment, and then you're going to draw 3 scaled box and arrow diagrams. It'd be really useful to use a ruler. I mean, you have to use a ruler. Draw a box and then add your key as well, so that the examiner would know what key you've used. The first one says a car moving forward when the engine provides 2,000 newtons of thrust. The second one says a sail on a stationary boat being pushed by the air with a force of 100 newtons. And the last one says a girl pulling her dad out of the road, just like we saw last lesson, with a force of 500 newtons. So if you can draw box and arrow diagrams with a ruler, and I'll pause the video for you now. Okay, so hopefully you've had a go at those. Let's look at some answers. So the first one, there's the box. And my key is going to be 400 newtons per centimetre. So 400 newtons into 2,000 is 5. So my arrow would be 5 centimetres long. And because the car is moving forward and the car engine provides the thrust, we've got the arrow coming out of the box going towards the right. Now you could have chosen whatever scale you wanted, whatever key you wanted, but that was my one that I chose. And as long as your one makes sense, then it would be perfectly fine. That's just one possible scale that I've used. And then all nicely labelled. There we go. Again, we draw the box for our stationary boat. I'm not going to have to draw a boat, we just draw a box. And for me, I've chosen 50 newtons per centimetre. So if it's 100 newtons altogether, then that's just going to be 2 centimetres long. So we put our ruler down on the table. And this one, it has the air pushing onto the boat. So the arrow is going to go from the right to the left because it's pushing the boat. It's like it's pushing the block. Don't worry if that one tripped you up. It's designed to. They are tricky, but you'll get lots of practice with these, don't worry. And then 100 newtons because I've written the magnitude there. And then the arrow provides the direction, So I can now represent this as a vector quantity. So let's have a look at the third one. A girl dad out of the road with a force of 500 newtons. So I've chosen 100 newtons for every centimetre. So 500 newtons makes 5 centimetre long arrow. And she's pulling her dad, so she'll be pulling the box, if you like. So the arrow goes from left to right. And this one would be 5 centimetres long. And there it is, labelled 500 newtons as well. There we go, perfect. How did you do? Right, let's have a look at the Sunday market then. So Isaac Newton understood lots about forces. I'm sure you've heard about him before. Forces has the unit Newton, so like 50 newtons or 100 newtons, because it's actually named after Isaac Newton. And he was very, very, very clever. He was able to figure out a lot of this for the very, very first time, so that we're able to understand it in our science lessons today. So here is Isaac Newton. There he is. Of course, we don't have a real picture of him because the camera hadn't been invented. And he's looking for an early bargain in Catherine Hill. Well, if he was alive today, maybe he would. So he says, and you need to be able to quote this, when two objects interact, the forces they exert on each other are equal and opposite. So Isaac Newton said, when two objects interact, the forces they exert on each other are equal and opposite. And that's Newton's third law of motion. So if you look at our objectives, it's the bottom one, the third one. And that's something that you need to be able to state off by heart. You also need to understand what it means as well. We'll go through that now. So last lesson, we learned about some forces. And the gravitational force causes the woman to be pulled down by the earth. But, and this is kind of weird, the woman also pulls the earth upwards with the same amount of force. And that's crazy. So because the earth is so massive compared to us, the earth is able to pull us down more than we're able to pull it up. But we do actually have an effect on the earth. When the gravitational force of the earth pulls us downwards, we do ever so slightly pull the earth upwards with us as well. So, because there's human beings all around the planet, it kind of negates that and the earth kind of stays where it is. But if we put all the human beings, say on the Isle of Wight, all at the same time, we all jumped, then some scientists have said that the earth would actually move upwards just a slight tiny bit. Very interesting. So we can see that the gravitational forces exerted on the woman and the earth are in opposite direction and equal in magnitude. So to represent this, we draw the arrows the same length to show that the magnitude or the amount is equal, and we show the opposite direction. So we draw the arrows going in the opposite direction. The gravitational force pulling her down and the woman pulling the earth up. So we make sure it's in opposite direction. Let's look at another example. So the man pushes into an air particle. There he goes. He's walking forward and he pushes himself into an air particle. Well, third law of motion says that when two objects interact, the forces they exert on each other are equal and opposite. So if he's pushing himself into an air particle, then the air particle must actually push back on him, equal in magnitude but opposite in direction. So again, we have the arrows the same length to show the same magnitude, but in opposite directions. Kind of crazy to think about. Every single air particle you hit when you walk, and then every single air particle is pushing you back in the opposite direction. So let's look at a bird. There he is. So the bird pushes down onto particles of air. I think you can figure out what's going to happen now. And the air pushes the bird upwards, giving it lift. So the wings push downwards onto the air, and Isaac Newton says forces that exert on each other are equal and opposite. So the air must push up on the bird, equal in magnitude, again, same length arrows, opposite in direction. And then up the bird goes. Okay, so we also try to explain this in terms of action and reaction. And I think this makes things a little bit easier, actually. So perhaps you might have gone to the Forum Sport and Fitness. You might have gone for a swim, maybe in one of your PE lessons. So let's have a look at this this makes things a little bit easier to understand. So when you swim, you push against the water. This is your action. Your action causes you to push against the water. And because you did that, the water reacts, or what's called the reaction force, by pushing you forward. Let's look at a little schematic. So this little diagram here shows your action force goes to the left. So the swimmer pushes the water in the backward direction. So you move your arms and you move your hand backwards onto the water. And because you've done that, the reaction force causes the water to exert a force on the swimmer, ultimately pushing them forward. So equal in magnitude, the arrows are the same length, but opposite in direction. So another good example is Bart Simpson. I love The Simpsons, getting up to no good. Let's have a look at this little GIF here. I wish we could do this in a science lesson. It'd be so much fun, wouldn't it? I wonder if you could figure out what's going on here. What's the action and what's the reaction? Well, the action comes from the fire extinguisher. So the fire extinguisher pushes air outwards with a great force, or maybe it's carbon dioxide perhaps, and that causes the air in the surrounding air, so outside of the fire extinguisher, to react and push Bart to the chair and the fire extinguisher in the opposite direction. So we have an action and a reaction. So what I've written is the extinguisher gas pushes forwards, that's the action, and the gas pushes the extinguisher backwards, reaction, making Bart go backwards. So your turn now. So can you see where the action and reaction forces are? So here's a quick 4 questions. All you've got to say is where the action and the reaction forces are and what's going on. So let's look at the example. We've got a baseball bat hitting a baseball. The action force, the bat pushes the ball to the right, and the reaction force, the ball pushes the bat to the left. So you might have done this. Maybe you've played badminton or tennis or cricket or hockey, and when you strike whatever ball it is that you're hitting, you might have felt that the bat or the racket actually goes in the opposite direction once you've struck the target. So for each of the examples, the boy sitting with an apple in a hammock, the lady pushing the boulder up the hill, the hammer hitting the nail, and the cube walking just on a flat surface. If you can name the action force and reaction force and see which way things are being pushed. So if you do this in your books, and then you're going to have to email this to your teacher. So this is where you should be pausing the video now so that you're able to do each of these and then email them to your teacher, and then we'll continue in just a moment. Okay, let's move on then. So I hope you've emailed that to your teacher now. So Isaac Newton also said one more thing about this. He said that if a body was in equilibrium, now that word equilibrium, if you look at the first 5 letters, almost looks like the word equal. So that's like an easier way to understand this. He said that if a body was in equilibrium, then the oppositional forces were balanced. So if a body was all equal, then all the opposite forces are balanced. If the body was not in equilibrium, then the oppositional forces were unbalanced. So what does this mean? So let's look at this man here. He's pushing on the table, which we now know is the action. It's his action of pushing on the table. And we know that the table is going to push back on the man. That's the reaction force. But neither are moving. Okay, so if his action force was greater to overcome the reaction force, then the table would be moved. So if it's not moving, the action and the reaction force must be equal. They must be in equilibrium. So the system stays where it is, nothing moves, it's stationary, and we say that all the forces acting on the body are in equilibrium. The table has to be pushing back on the man with the same force with what he is pushing onto the table. The action and reaction must be equal. They must be in equilibrium. So, here are your final tasks, like we did last lesson. You're going to have a few tasks to do. You just do them in your book, and then you can email these to your teacher. So task 1 is define scalar vector in Newton's third law. Task 2, draw a free body diagram for you sitting on one of the new seats at the Westway Cinema. So free body diagram, draw a box and an arrow diagram. See if you can think about if you'd be stationary, would you not be, would your forces be in equilibrium, would they not, would the arrows be the same size or not, would they be in opposite directions or not. Task 3, in 3 bullet points, explain the difference between a scalar and a vector. And I'm sure you'll be thinking about things like magnitude and direction. Maybe give a couple of examples. Task 4, draw a labelled free body diagram for an activity that you see at the Froome Festival. So you can choose whatever you want, box and arrow diagram, and perhaps you could say if it was in equilibrium or not. Task 5, draw a labelled action-reaction diagram for a sporting activity you do in PE. You can choose whatever you wanted. Netball, hockey, track and field, athletics. It could be anything, couldn't it? Task 6, a dog is moving forward with a force of 300 newtons. The air pushes back on the dog with a force of 300 newtons. So draw a diagram to show if the dog is in equilibrium. Okay, so box and arrow diagrams. See if you can scale that arrow, write down the key, and then determine if the dog is in equilibrium. Task 7, summarise this whole lesson like we did with the Cornell method, like we did last lesson, or the postcard physics. Title along the top, keywords and definitions in the margin. Break up the lesson summary, free body diagram example on the page, and then underneath anything that you are unsure of. Okay, and just double check that you've got your work from the action-reaction diagrams, and this does need to be emailed to your teacher. Okay, thanks for listening. Take care, everyone. Stay safe.